Up until now, most of what we have covered was preliminary information and tasks to get us to this point. Next, I'll cover the Productivity 3000's PID Loop instruction, the main focus of this video series. Once I have my analog signal scaled to usable and understandable values, I can now create my PID loop instruction that will perform the calculations. I click and drag the PID loop instruction located towards the bottom of the instructions list under the PID heading and drop it on the next available end rung in my ladder editor window as shown here. The PID loop configuration window will open with the major setup tab ready for the various tag names and parameters to be entered. I enter a name for the PID loop in the loop name text box. I have chosen water volume control. Continuing with the PID loop configuration using fill in the blank parameters, I enter the tag name tank_volume_SP into the set point parameter and select the tag name tank_volume from the drop-down list that was defined earlier for the process variable. For the input range max parameter, I select the tag name maximum_volume that I calculated earlier, and likewise the tag name minimum_volume that was also calculated is entered for the input range min. I continue adding parameters to the fill-in-the-blank boxes. The pump_speed tag name I set up in channel 1 of our analog output module is used for the process output parameter. The output range max parameter is set to 65,535 and the output range min parameter is set to 0. I use the same values for the output upper limit and output lower limit parameters in my application. In the next area, I will set up the tag names for our proportional gain, integral reset time, and derivative rate time parameters. To keep the naming simple for our example application, I have used the name of the parameter as the tag name, so I can enter proportional for the proportional gain, integral for the integral reset time, selecting seconds for my time range, and derivative for the derivative rate time with a default time in seconds. Before I press the OK button to accept our PID loop, let me mention the other tabs available within the instruction window that will be covered in future Learn videos. These include the Major Advanced tab, which for our example application we have used the default sample rate of 500 milliseconds, a forward process action, freeze bias is checked, and although we will discover that our application does not require any derivative, the default for base the derivative on the process variable is checked. The Major Alarms tab can be used to alarm values and bits for various conditions that occur during the PID loop operation. The Minor Setup, Minor Advanced, and Minor Alarms tabs are used if we had chosen a cascade mode of operation found under the Major Advanced tab. Cascade mode is typically used in applications where a secondary process can directly affect the primary process through either the effects of disturbances from the secondary process or when the process gain or output actuator is nonlinear. Once all the tag names and parameters have been entered into the PID loop instruction, we can press the OK button. The next window that pops up will be the Define Tags dialog window, giving us the opportunity to select the data type for each of our new tag names. The default data type for all of the new tag names is integer 32-bit. I will leave the default for the proportional, integral, and derivative tag names, but select float 32-bit for the set_point tag name. Next, I transfer the changes to the Productivity 3000 CPU, save the project, and then enable the monitor mode so I can see my results up to this point. Taking a quick look at our tag database and using the checkboxes to select the various data types, we see 32-bit floating point and 32-bit integer data types were assigned to the tag names used in the PID loop instruction. A 32-bit integer data type was chosen for the proportional, integral, and derivative terms. The 32-bit integer has plenty of resolution for the values that are typically used for final tuning of the PID loop. As seen in our final commented PID loop rung, the PID instruction box requires 2 lines of control. The first is for enabling the PID execution, and the second for setting the PID to automatic mode or manual mode. Discrete bits controlled from push buttons located on the See More touch panel are used to enable the PID loop and also for placing the loop in auto mode. When the PID loop is not in auto mode, it is in manual mode. We will see how manual mode is used for our initial startup, manually tune our PID loop, and then auto tuning the PID loop with the software's built-in PID tuning feature. In the next video, part 8, we will cover some of the miscellaneous ladder logic that was created to add some extra monitoring features to our project.